Okay, then let's continue with the last talk of the afternoon. It's a pleasure to have Tamas GOMBOR, who will talk about exact overlap for boundary states. Okay, thanks.
Thank you, Marius. So I'm working on this calculation and prove overlaps for boundary states for 5 years now, and recently I reached the important milestone. So now I have exact overlap formulas for any integrable matrix product states for any rational spin chain. So I will show these results today. After a very short motivation, I will start with the simplest case, so overlaps of the two side states for the GL2 spin chain. And after that, I generalize for the nested spin chain, GLN. And after that, I generalize the state for, to the matrix product states. So why are we interested in boundary states and the corresponding overlaps? So this research started at 10 years ago in two different parts of the theoretical physics independently. So one application is these overlaps are input in the studies of non-equilibrium dynamics in statistical physics. And the other application is that the overlaps corresponds to one-point function of defect theories. Okay, let's start with this two side states in GL2 spin chain. So the overlaps can be graphically interpreted in this way. So we consider the rational 6-vertex model, and the weights are given by entries of the Lux operator, and this black line corresponds to quantum space, and the red line is the auxiliary space, and the auxiliary space is a two-dimensional one, so spin 1/2, and the black line can be any representation, including infinite-dimensional ones. And we want to calculate this partition function, which depends on the inhomogeneities, thetas, and this inhomogeneities comes in pairs, so θ1 minus θ1 and so on, and also we have u beta roots. And we introduce the monodromy matrix and beta states, which is the action of the T12 element of the monodromy matrix, and we also have pseudo vacuum. And this is the boundary state. So this is a two-side state. It's a tensor product of this elementary state phi, which depends on the inhomogeneity. And this is the graphical notation. So this is a two-side state. So we build the boundary state as a tensor product. And this partition function is equivalent to this overlap. And we also introduce a K matrix, which is a matrix in the auxiliary space. So this is a 2x2 matrix. And the integrable boundary state is defined by this KT relation. So this is the graphical representation. So this is the transfer monodromy matrix, K matrix, and the boundary state. So basically, using this K matrix, we can change the sign of the spectral parameter of the monodromy matrix. And we already saw this relation in the first talk of this conference. So Ruben showed this relation, and it defined the boundary Youngian invariants. So this is a connection to the first talk. And let's see the most important properties of this KT relation. First, we know that the monodromy matrix satisfies the RTT algebra. And let's see product of two monodromy matrices with different auxiliary spaces, 1 and 2. And at first, we can use the RTT relation to change the order of the t's, and after that, we can use the KT relation to change the size of the Z2, and after that, we can use the TT relation again and use the KT relation again. And at the end, we obtain an expression where the signs of the z's are changed. But we can obtain this term in a different order, so at first, use the KT relation to change the size of the z. After that, we use the RTT and the KT and the RTT. And we obtain a different expression with different coefficients, but these two expressions should be the same, and this is equivalent to the reflection equation. So this K matrix is cannot be anything, arbitrary matrix, so it should satisfy the reflection equation, or boundary Ambaxter equation. And this two-side state phi is also a reflection equation, but it corresponds to another representation, which is the corresponds to a quantum space. So it's a higher representation K matrix. Okay, and let's see what is the consequence for the on-shell overlap. So let us define the transfer matrix without twists. And the KT relation is equivalent, or not equivalent, but we can derive this simpler equation from the KT relation. The product with the inverse of the K and taking the trace in the auxiliary space. On-shell beta states is an eigenvector of the transfer matrix. And so we can apply this relation to, on the beta states, and the on-shell non-vanishing on-shell overlap requires this condition for the eigenvalue, and this is equivalent that the beta roots should satisfy this pair structure. This means that the set of beta roots is equal to the set with the opposite signs.
What is the relation between the red K matrix and the black K matrix?
Red K matrix?
Yeah, so the one in the auxiliary space and then there's the one in the quantum space. So they're totally independent?
No, so if you, the quantum space is finite dimensional, you can obtain this black K matrix with fusion, for example, from the Revlon. Now let us calculate the off-shell overlaps, and for this we use the KT relation. The KT relation is a 2x2 matrix in the auxiliary space, and we only use this 2-2 component. The 2-2 component looks like this, and assuming that this component of the K matrix, so this K21, is not 0, then we can express this term with these others, and we know that this T12 creates beta roots, and the diagonal element does not change the number of beta roots, and this T21 annihilates beta roots. So we use this relation to change the creation operators in the beta states to annihilation ones. So we can apply this relation to the off-shell overlap. So the beta states is just the product of T12s, and we also introduce the pseudo-vacuum eigenvalues, which decodes all the information on the quantum space. Okay, so if we start with overlap with R+1 beta root, then we can replace this T12 with these operators. And now we can use the RTT relation to express this action. And finally, we will obtain the sum of overlaps, but these overlaps have less beta roots than the one in the left-hand side. So this is a recursion relation for the off-shell overlap. So this defines completely the off-shell overlap. And we can use this recursion to derive important properties of the off-shell overlap. The first one is the sum formula. So this is a linear combination of monomials of the pseudo-vacuum eigenvalues, and the coefficients W does not depend on lambdas. So basically this W depends only on the algebra, and this lambda part depends on the representation of the quantum space. And this weight factorized in this way, and these are the highest coefficients, and we can derive recursion relation for these highest coefficients. And these properties can be derived from the KT relation, the recurrence equation for the off-shell beta states, action formula, and coproduct formulas. More precisely, we use the KT relation to change the creation operator to annihilation one. Recurrence equation is simple in this GL2 case. And the action formula tells us how act on the monodromy matrix entries on the beta states. And we also have coproduct formula. So if we have these four input, we can derive these properties. And this property is enough to derive the on-shell formula. So let us take the on-shell limit. For the on-shell beta states, the beta roots satisfy the beta ansatz equation. We can define the Godin matrix. And we know that the on-shell norm is proportional to the Godin determinant. And this can be proved by Korepin's criteria. Now, for the on-shell state, we have the pair structure. Therefore, we can divide the beta roots in two sets, where this, in the pair structure limit, this U minus is minus U plus. And we can define two Godin-like matrices. And the original Godin determinant is factorized in this way. And we can generalize the Korepin criteria for the boundary state overlap, and we can show that the on-shell overlap is proportional to this Godin line determinant. The normalized on-shell overlap has this form, where this blue term, ratio of Godin determinants, is completely independent on the boundary state. It depends only on the beta state. And this red part is a product of one particle overlaps. And this one particle overlap function Fu depends on the boundary state only, and or equivalently the K matrix. So because we use only just the KT relation, this F is determined by components of the K matrix, and it's independent on the representation of the quantum space. For the GL2 reflection equation, the general solution of the boundary and boxer equation has this form, and so we can parameterize with this way. And for this parameterization, this one particle overlap function looks like this. Okay, so at this point, I think I take a little detour because today we already saw overlap formulas. So in the morning, Simon and Paul also show how the overlaps looks like, and I want to summarize the connection and the differences between my results and their results. So in my work, I define the transfer matrix, just simply the trace of the monodromy matrix, so without any twist. And we show that the beta roots have this pair structure. Okay, sorry. Yeah, so, and we can introduce also the Q function, so Q, and this relation is equivalent to that the Q1 it's worse. So it's just.
Tamas, the other black marker might be more useful.
Okay, thank you. Thank you. So in the level of the Q function, this pair structure tells us this Q1 is symmetric or anti-symmetric depending on the number of beta roots are even or odd. Okay, and then yeah, so and now the overlaps are determined only with the roots of this Q1, and the Godin matrix factorize, and this G plus and G minus defined with this pair structure, so this decomposition. And the talk in the morning, they introduce a twisted transfer matrix. And in this situation, it turns out there is no pair structure, but there is a generalized version. So they use also Q1 and also Q2. And it turns out that the Q1 is just the Q2 at minus U. And it also, there is a sign depending on how many beta roots we have. So this is the generalization of the pair structure. But the Q1 root has no pair structure, therefore this definition, it doesn't exist anymore. So for the twisted case, we cannot have this Godin-like determinant formula. So in the twisted case, we should have formulas like it was shown Simon and Paul's talk. So this is so this is a significant change in the overlap business when you add the twist. So it completely changes everything. And in this talk, I will concentrate on only this setup. So when we have an untwisted transfer matrix and beta states. Okay. So now I continue. Okay, so this was the rank 1 case. Now we go to higher rank. So now we have n-1 type of beta roots, and this is my notation for the beta state. And now, so we want to generalize the KT relation. And in this situation, we have two types of KT relation, the twisted and the untwisted. But this twisted means different thing than the twist before. So now I don't use any twist in the definition of the transfer matrix. The twist means that we have boundary states satisfying this equation or this. So this untwisted equation is the same as before, but now we can also introduce another monodromy matrix, T hat, which is just the inverse of and transpose of the original one. And we can think that this T hat is just the charge conjugated monodromy matrix. And this also satisfies the RTT relation, so on. Okay, and we can do the same calculation as before and derive the compatibility condition with the RTT, and we obtain two types of reflection equation, the usual boundary Young-Baxter equation and the twisted boundary Young-Baxter equation. Let's see the classification of the solution of the untwisted boundary Young-Baxter equation. The general solution has this form, and this A matrix can be diagonalized, and because the A square is 1, the eigenvalues are plus or minus 1s, and the number of minus 1 is m, then the residual symmetry of this K matrix is GLM plus GLN minus m. For the twisted boundary Young-Baxter equation, the solutions are just constant matrices, and this constant matrix is symmetric or antisymmetric. For the symmetric one, the residual symmetry is ON. For the antisymmetric one, is SPN. And let's see what happens in the on-shell limit. So for the non-vanishing on-shell overlaps, the eigenvalues satisfy this condition, and this means the beta roots satisfy this pair structure. So this beta roots are coupled with respect to the Z2 automorphism of the Dynkin diagram. So the first U is the first beta root set is equal to the last with opposite sign. So this is the achiral pair structure. And for the twisted KT relation, the non-vanishing overlaps require this other pair structure where every set of beta roots are equal with itself by a minus, with the minus sign. So every node is paired with itself. Okay. Now we can repeat the calculation of the off-shell overlap, and we want to derive the similar properties of the off-shell overlap. And what is needed for this calculation? KT relation to change the creation to annihilation operators. And we need a recurrence formula for the off-shell overlap. We need the action formula. We need a product formula. And luckily, these three ingredients exist. So this list of papers, it was determined. So I used these results to derive the properties of the off-shell overlap. And we can derive this very similar recursion relation for the U1 roots. So using recurrence relation and after the KT relation and after the action formula, we obtain recursion where we decrease the numbers of the first type of roots. And we can eliminate the first type of roots and continue the nesting. And this determines the off-shell overlap. And these properties can be used to derive the on-shell formula. So using the Korepin criteria and the properties of the off-shell overlap, we can derive that the off-shell normalized on-shell overlap has this form. And now this G plus and G minus depends on the type of the pair structure. So it looks different for the achiral and the chiral pair structure. And the boundary dependent part is this F functions are given by the K matrix. And these are the concrete answers. For the untwisted boundary states, this is the general overlap formula. And here I use the Q functions. And in this formula, we have a chiral pair structure. And for the twisted situation, we have these two types of overlaps. And in these formulas, we have chiral pair structure. Okay. So this is the final answer for the GLN spin chain with two-sided boundary states. So now we generalize this method for the matrix product states. So now we introduce a bond or boundary space. And the boundary space is indexed by alpha and beta. And the matrix product state is built from this matrix M, well, a set of matrix. And this I index corresponds to the quantum space, and every Mi is a matrix in the boundary space. So graphically, this is a three-leg object. And in this definition, so we obtain this state. So for every alpha and beta are indexes in the boundary space. So this product of M is a matrix in the boundary space. So basically we have a matrix of states. And I also introduced this compact notation. So this generalized boundary state is a covector in the quantum space and matrix in the boundary space. And we also introduce a K matrix, which is a matrix in the auxiliary space and the boundary space. And this is the graphical notation for the K matrix. So it has 4 legs. This red one corresponds to the auxiliary space, and the yellow one corresponds to the boundary space. And this is the generalization of the KT relation. So now we have a monodromy matrix and a boundary state and a K matrix. And so we have 3 types of states, auxiliary, quantum, and boundary, and these 3 objects act only 2 of them. And this is a natural generalization of the previous KT relation. So only difference is now this Kij components are not the scalar, but a matrix. And we also introduce the periodic matrix product state, which contains only which contains a trace in the boundary space. Okay. Now we can repeat the compatibility calculation between the KT and RTT, and we obtain reflection equation for the K matrices. And now the K matrices are non-trivial representation of the reflection algebra. So this boundary Yang-Baxter equation defines the reflection algebra. Now the K matrices are higher dimensional representation of this reflection algebras. And what are these reflection algebras? For the untwisted boundary Yang-Baxter equation, we have this BNM algebra, which have residual symmetry GLN plus GLN minus M. And for the twisted boundary Yang-Baxter equation, we have two twisted Yangian algebras, Y plus and Y minus, and these have residual symmetry ON and SPM. We can calculate the off-shell overlaps, and I show what happens for the twisted KT relation. So we saw previously that we can eliminate creation operator if one component of the KT relation is not zero. Now this is a matrix, so now we have to assume that this matrix is invertible. So in this twisted situation, this K11 has to be invertible. And if a component is this matrix is invertible, then we have a recursion for the U1 roots. So we obtain this type of recursion, so we can eliminate all U1. So we can express the general overlap with the sum of overlaps of GLN minus 1 overlaps. And the question is how this recursion continues. So what is the KT relation for this second level system? So we can get this block form of the K matrix. So this is the first column and first row. And the first guess would be this GLN minus 1 K matrix is this block. But it turns out it does not satisfy the KT relation in this subsector. But we can introduce a nested K matrix, which is just a combination of this green and green block and then this column and row in this way. And it also contains the inverse of the K11. And this nested K matrix is the GLN minus 1 K matrix. And using this matrix, we can continue the nesting. And it can be also show that this K11 component commutes with all the components of the nested K matrix. So this is the sketch of the nesting. So every level we introduce new K matrices, and we introduce these G operators, which is the left top elements of this nested K matrices. And because this element is commutes with the higher level K matrices, these G operators are commutes. So this is a Cartan subalgebra of the twisted Yangian. And the only condition for this method is the assumption that this K11 is invertible. And it turns out for this Y plus algebra, this inverse exists. But for the other twisted Yangian, it doesn't exist. But we have another type of recursion we start with not the U1, but the U2. And then this is the sketch of the recursion. So we eliminate first the second node. And using this new recursion, we can also define G operators which commutes. And so this was the twisted case. And we have also untwisted boundary states. For the untwisted situation, we have another type of recursion. So So for the untwisted situation, we eliminate simultaneously the first and the last node. And we have this nesting. So for starting with the GLN chain, we derive the problem to the GLN-2 chain. And every level we obtain, we define new and new nested K matrices and G operators. And these G operators are commuting. And for the on-shell overlap, we define this combination. So this combination is, does not depend on the normalization of the K matrix. And of course, these F operators are also commuting. Therefore, we can choose a diagonal basis for these F operators. And the normalized on-shell overlap for the periodic matrix product state, the overlap looks like this, and the spectrum of this F operator goes to this formula. So now it's not a factorized form, but a sum of the previous expression. And there is also an additional normalization which comes from the norm of the beta state. So this is the final formula, which works for every GLN integrable matrix product state. And I also extended these formulas for other rational spin chain. And we know every type of reflection algebra have a recursion which defines the G operators. And I worked out every type of nesting for every rational reflection algebra. And this is the list of the possibilities. And I have nesting for every type. And I also extend it for the graded situation. So I have two conclusions. So one is the matrix product states are equivalent to K matrices, and the K matrices are representation of the reflection algebras. And we define a Cartan subalgebra for these reflection algebras. And the on-shell overlaps has this form where this F is just the eigenvalues of the operators F. And the other conclusion is, if somebody wants to prove this formula, then for the proof, there is 4 necessary conditions. We have to know the KT relation, which change the creation operator to annullated ones. We have to know the recurrence formula for the off-shell beta vector. We have to know the section formula, and also we have to know the coproduct formula. And if we know these 4 ingredients, we can derive any of these overlaps. So thank you for your attention.
Thank you for the nice talk. Are there any questions?
Thank you for the very nice talk. If I remember correctly, in your paper from a few years ago with also with Balázs and Marius, when you were looking at these overlaps in defect CFT, you had some type of overlap formulas in matrix product states where the red piece, the part which depends on the boundary, if I remember correctly, was expressed in terms of some sum of transfer matrices and some weird representations. Do you have maybe some similar interpretation for these Fs? Are they somehow related then to transfer matrices?
Somehow it can be related, but so sometimes it exists, but sometimes not. So it depends on what is the representation of the twisted Youngian. So you know that you can obtain twisted Youngian representation by getting the Youngian representation. With this twisted Youngian is just the coming from the Youngian representation. Then this prefactor is just the transfer matrix eigenvalue. But for representation, which are not simply just the representation of the original Youngian, then in this situation, you have a more general form. Sometimes it also can be expressed by a linear combination of transfer matrix eigenvalue, but there are some examples when this is also not available.
So I've got a kind of open question. You and maybe some people in the audience, we saw this KT relation appear, and also another talks Q operators appearing in the kind of floating around. Is there a KQ relation? And if there exists, would it have any role in meaning? Right?
I don't know.
It should be. It should be. Someone should find and figure out what does it mean. I need motivation to look for it.
So the nice talk. So my question is that this is the rational case.
Yes.
So for how about for the trigonometric case with the k-matrix with off diagonal elements case? What's the results is?
So actually, in this situation for rational case, so I always consider when the K matrix is most general as possible. So every component is non-zero if it's possible, and then this situation everything works fine. But if some components are zero, then you need to do some tricks.
For trigonometry.
So in this situation, so in the work with algebraic beta ansatz, so the diagonal K matrices are the best or easy, but here no. So now the off diagonal K matrices are easier. So it's an interesting situation.
Mostly works in the same way, but not always.
But for the Russian case, actually you use the same every K matrix you can use the similarity G and G inverse to reduce to the diagonal ones.
Yes.
But for the trigonometric case, doesn't work. I just asked the question.
Yeah, but in the trigonometric case for the XXZ case also the most general K matrix has I don't know 3 or 4 parameter and I use this most general parameterization where all the K matrix entries are not zero. Then I can apply this formulation to derive the overlap. So I don't know for a higher rank case what is the most general K matrices. The problem appears when the most general K matrices contain zero element, which is crucial in this calculation. But I don't know how the most general K matrix looks like in a nested trigonometric case.
Yeah, it's all in my paper.
Yeah. Okay, I know where to find, but
Yeah, but what we're saying is correct. In some cases, that gauge freedom helps here. And in trigonometric case, there's less gauge freedom, but it might make some cases more complicated. But that would just mean like more techniques would be required.
Yeah, but for the XXZ case, this technique can be applied.
For XXZ that's fine, but for higher rank, there might be some.
Yeah, but for higher rank also need
Even
other
here.
ingredients, so like recursion and action formula and coproduct, which I
There are
don't
some
know if
bigger fish
exist
to
or
fry
not.
yet.
So I really like this comparison you did, but just one comment. So I think if you take the second twisted case and you remove the twist, then Q1 is equal to Q2.
Yes.
So then if you have the twisted formula, you can take the limit, you get back to your first set of equations, right?
Yes.
Okay.
But so it's trivial to take this untwisted limit of your formulas or not?
It requires a lot of power expand in Mathematica, but
okay,
but
so in
otherwise,
principle it's manageable. Okay.
yeah, potentially.
Yeah. So in principle, from your results can be get my, but from my, it's obviously not go there because my quantities doesn't exist. But anyway, so my results is more general because it contains all the MPS and.
Okay, so may I also have a small question, but I missed in your talk why the coproduct formula is important. I understand the three first, but
yeah,
could you recall me?
Just skip this part. Yes. So these are the properties of the off-shell overlap, and we have this second part when we prove that these weights are factorized in this form, and this second equation is derived from the coproduct formula.
And another question, so if the boundary state, you just say it's a boundary state that satisfies this Kitty relation. So you never use rotation, etc. But it's why you don't care about diagonal. But I don't understand. Yeah, I understand why non-diagonal you could not make the recursion, basically.
So I have to use a rotation to get non-zero elements for a specific point. So when I have so this relation. So this is the heart of the calculation. So I have to express the creation operator, and there is always a special components of the K matrix, which appears as a coefficient before this term, and this term should be not zero. Yeah. So if it's possible, I use a global rotation to make this component not zero, and I can divide by this term, and then write recursion relations. But sometimes, so for example, if you have a singlet state, when the boundary state has zero spin, then if you calculate correctly the K matrix is diagonal. So these off-diagonal terms are not zero. And for these states, this method directly cannot apply it, but this singlet state always can be deformed to a non-singlet state. So the most general solution of the K matrix looks like this. I don't know it's readable or not. So there is an identity. So basically for a dimer state, so singlet state, the K matrix is this one. And but you can deform the states. And the deformation preserves integrability. So add this A, which is not an inverse, and now you can rotate to this A matrix get a non-zero 2-1 component. So this is the strategy.
And you say that the direct limit from the final formula to the diagonal case is not trivial, or not? I don't, because the Godin formula, you have ratio of Godin's F function. So you can say, let's start with non-diagonal matrix. I find the result and look to the limit at the end. It works well for the limit. It's trivial in the formula, more or less.
Yes, because the Godin determinant doesn't contain any parameter of the K matrix. So only just this prefactor depends on the K matrix, so every parameters here that is a combinatorial or prefactor before the overlap, and you take the limit, you always obtain that so it's vanishing or not if some quantum numbers satisfy some relation. So for example, for a singlet state, obviously we have a extra selection rule that the number of beta roots should be half of the size of the spin chain. So if this selection is satisfied, then the overlap is non-vanishing, and for other states, the overlap will be vanishing. So when you have these singular solutions, then always you have an extra selection rule.
Thanks.
Any further questions? If not, then I have one. So you said that it also extends to super algebras. So does it also extend to non-standard super algebras like centrally extended SL2/2 or D21 alpha?
No, so I wrote where I extended the formula, so this usual GL/M, so the general linear and the orthosymplectic. So I skipped this exotic ones.
Okay, thanks. Any further questions? Then if not, let's thank Tamas again.